Summary of domains and ranges of inverse trigonometric functions. Hello everyone. Let's begin with our summary of the domains and ranges of inverse trigonometric functions. Up until this point in our lessons, we have spent time examining each inverse trigonometric function individually to understand how they behave. As we discussed previously, trigonometric functions are periodic, meaning they repeat their values in regular intervals. Because of this repetition, they are not one-to-one functions, which normally makes it impossible to create a true inverse. To overcome this, we learned that we must restrict their domains to specific, smaller intervals. By doing this, the functions become bijective, which allows us to mathematically define their inverses. This current subsection is designed to serve as a comprehensive consolidation of all those restrictions we've studied, bringing everything together in one place. It is critical that you fully understand the concepts of the domain and the principal value range. This is because the domain determines whether a given input is mathematically valid, and the principal value range ensures that the output we get is unique and consistent. We will clarify these terms and look at a detailed summary table in the upcoming slides. 1. Understanding the terminology. Now that we have established why we need to restrict the domains of trigonometric functions to make them bijective, let us pause before we dive into the summary table. It is essential that we first clarify two fundamental terms that will be central to our discussion. Now that we have established why we need to restrict the domains of trigonometric functions to make them bijective, let us pause before we dive into the summary table. It is essential that we first clarify two fundamental terms that will be central to our discussion. First, let's look at the domain. In simple terms, the domain represents the set of all possible input values, which we usually denote as x, for which the inverse function is actually defined. It is important to keep in mind that if you provide a value that falls outside of this specific domain, the function is undefined, meaning it is mathematically impossible to calculate a result. Next, we have the principal value branch, which is essentially the range of the function. As we mentioned in the previous slide, trigonometric functions are periodic, which means a single value could potentially correspond to infinitely many angles. To ensure that our inverse functions provide a unique and consistent output, mathematicians have agreed upon a standard interval for the result. This specific, restricted range is what we call the principal value branch. Consequently, any value that you calculate which falls within this specific range is known as the principal value. Once you are comfortable with these two definitions, we will be ready to move on to the comprehensive summary table in the next slide. 2. Comprehensive summary table. Now that we have clarified the terminology regarding domains and principal value branches, let us examine this comprehensive summary table. This table consolidates the restrictions for all 6 inverse trigonometric functions, serving as a vital reference for your calculations. Starting with inverse sine, denoted as sine inverse of x, the domain is the closed interval from -1 to 1. Its principal value range is the closed interval from -π/2 to π/2. Next, we have inverse cosine, or cosine inverse of x. You will notice it shares the same domain as the inverse sine function, which is the closed interval from -1 to 1. However, its range is different, spanning the closed interval from 0 to π. Moving on to inverse tangent, written as tangent inverse of x. Unlike the first two, the domain here is the set of all real numbers. The principal value range is the open interval from -π/2 to π/2. Please note the open parentheses here, which indicate that the endpoints are not included. Similarly, for inverse cotangent, or cotangent inverse of x, the domain is also all real numbers. Its range, however, is the open interval from 0 to π. Now, let us look at the reciprocal functions. For inverse secant, denoted as secant inverse of x, the domain consists of all real numbers except for the open interval between -1 and 1. The range is the closed interval from 0 to π, excluding the value of pi over 2. Finally, for inverse cosecant, or cosecant inverse of x, the domain is the same as the inverse secant. All real numbers excluding the open interval from -1 to 1. The range is the closed interval from -pi over 2 to pi over 2, excluding 0. I encourage you to study this table carefully. In the next slide, we will apply this information to a practical example to determine whether a given mathematical expression is valid or undefined. 3. Conceptual application: validating inputs. Now that we have reviewed the summary table, let us look at how to apply that information in practice. Specifically, we will focus on the process of validating whether a mathematical expression is legal or mathematically defined. To put this into perspective, think of how a scientific calculator behaves. If you attempt to calculate the square root of a negative number, the calculator will return an error message because that operation is not defined for real numbers. We must apply the same logic when dealing with inverse trigonometric functions. Let us walk through a concrete example. Suppose we need to determine if the expression inverse sine of 1.5 is defined. Step 1 is to identify the function. In this instance, we are dealing with the inverse sine of x. Step 2 requires us to refer back to the domain listed in our summary table. For the inverse sine function, the domain is the closed interval from -1 to 1. This means that for the function to be valid, the input value, x, must be greater than or equal to -1 and less than or equal to 1. In step 3, we compare our specific input value to this domain. Our given value is 1.5. Finally, in step 4, we reach our conclusion. Since 1.5 is greater than 1, it falls outside the permitted interval of -1 to 1. Consequently, the expression inverse sine of 1.5 is undefined. Understanding this validation process is essential, as it prevents the common errors we will discuss in the next slide, particularly regarding the distinction between different types of brackets and notations. 4. Common mistakes to avoid. Now that we have reviewed the summary table and practiced validating inputs, it is important to address some common pitfalls that students often encounter when dealing with domains and ranges. First, let us discuss the notation of brackets. Please pay close attention to the difference between square brackets and parentheses. When you see a range written with square brackets, such as -pi over 2 to pi over 2, it indicates that the endpoints are included in the set. Conversely, a range written with parentheses, such as -pi over 2 to pi over 2, means the endpoints are excluded. For instance, the inverse tangent of x can never actually equal pi over 2, because the original tangent function has a vertical asymptote at that point. Next, let us address a very common error known as reciprocal confusion. Some students mistakenly assume that the inverse sine of x is equal to 1 divided by the sine of x. It is crucial to remember that the inverse sine of x is the inverse function, which is used to find the angle. On the other hand, the reciprocal of the sine of x, written as sine of x to the power of -1, is actually the cosecant of x. Finally, be careful not to mix up the ranges of the inverse sine and inverse cosine functions. Keep in mind that the range for inverse sine is centered around 0, spanning from -pi over 2 to +pi over 2. In contrast, the range for inverse cosine is strictly non-negative, spanning from 0 to pi. 5. Key takeaways. To wrap up this section, let us review the key takeaways to ensure you have a solid grasp of these concepts. First, as a reminder of our earlier discussion on terminology, the domain represents the set of all allowed input values, while the range, specifically the principal value branch, is the set of possible outputs. Looking back at our summary table, you will notice that inverse sine of x and inverse cosine of x share the exact same domain, which is the closed interval from -1 to 1. In contrast, inverse tangent of x and inverse cotangent of x are more flexible, as they accept any real number as an input. Then we have inverse secant of x and inverse cosecant of x. These two functions accept values that are either less than or equal to -1, or greater than or equal to +1. Finally, as we demonstrated in our example with the value 1.5, always make it a habit to check the domain first. This ensures that the expression is mathematically valid before you attempt to calculate the principal value.